Good evening, everyone. So today is the eighth class of stochastic processes. Um, Today's lecture 8. Today also we'll be going through some Poisson processes. We'll be covering some topics in Poisson processes such as uh, non-homogeneous Poisson processes, compound Poisson processes, and we'll also be covering splitting and merging of Poisson process. So first we'll do a small recap of what we have done. So we first defined a stochastic process, which is a collection of uh, natural numbers uh, for any time t. This is said to be a counting process. Uh, Now this counting process is a Poisson process if it has the following properties. So we had two definitions. Our definition one was uh, one n of 0 equal to 0. Two, process has independent increment. So each non-overlapping section of time, the number of events occurring in each non-overlapping section of time would be independent of each other. The third one is the number of events in any interval of length t is Poisson distributed. With parameter lambda t. So as you increase the length of the interval that you're observing, the expected number of events that will happen in that interval will increase because now you're looking at more, you're covering more area, so the probability that your event will occur in a bigger area is very high. So mathematically, the third um, point can be written as probability of n p plus s minus ns equal to n. So what does this mean is, so what does this mean is, if you have interval from s to t plus s, where this interval is of length t. Now you want to find the probability that in this interval only n events occur, that according to the point number 3 of the definition is it is Poisson distributed with parameter lambda t. So it is e power minus lambda t power n by n factorial, where n is some natural number. It belongs to natural number, and also 0. You can also have 0. So from this, what we can say is the third property also gives us an extra property, but you don't need to define it separately because third and the first and the second together give that they have stationary increments. So two non-overlapping intersections with the same length will have the same distribution. So you look at the same length at anywhere, it will have the same distribution. And also, since it is Poisson distribution, we know that the expectation of the Poisson distribution is the parameter itself. So expectation of NT equal to lambda t. So lambda is the rate of the process. Sorry for okay. Then we also saw there's a second definition for the Poisson process. So there was definition two. Second definition, we saw that again you have a counting process NT such that t greater than or equal to 0. Now this counting process is a Poisson process if one n of 0 equal to 0, two, process has stationary and independent increments, and three, the probability of the number of events in a very small interval delta t is 1. So one event happens in a very small interval of delta t is lambda into delta t plus order of h, where order of h is a function. F is said to be OH if limit h tends to 0, fh by h equal to 0. This is the meaning of order of h. And fourth property is property that in a very small interval, the probability that number of events happening in a very small interval is greater than or equal to 2 is of the order delta t. Okay. So next we saw how to show the equivalence between these two definitions. We showed it only one side. We showed it for so definition. The second definition implies the first definition. So if you know that the second definition is true, then how do you get the Poisson distribution for each interval? Uh, then we also saw how counting why it is good to model counting process as binomial process as Poisson process because Poisson is an binomial is an approximation of Poisson, and you use the binomial to approximate the counting the number of cars that have passed through or the number of events that have occurred. So binomial distribution is an approximation of Poisson distribution. So from there we have the notion of why we need to model counting process a Poisson process. Then we have interval, and then we also saw another way to um, represent the Poisson process, not just by the counting the number of events that happen in an interval. You can also describe the counting process by, or the Poisson process by, um, finding the distribution of the inter-arrival or the arrival times. So we also defined inter-arrival times. These we called as size. These were IID, and the distribution was exponential. Next, we could also model them using arrival times. Arrival times we denoted with SI. This was Erlang, and SN, the nth arrival time, was given by summation I equal to 1 to n xi. And these had two parameters, n and lambda, where n was the shape parameter and lambda was the rate parameter. We found the distributions of these both. We said that even defining the interval times or the arrival times or the waiting times, you can also characterize the Poisson process. And the most important relation in the Poisson process, connecting the number of events that have occurred in an interval and the arrival times, was given by. So we saw that the events n t is greater than or equal to n is the same event as saying that Sn is less than or equal to t. We saw this implication. Mm. Then we saw about order statistics. So in the order statistics, we saw that, so if you have um, x1 to xn IID random variables with some distribution, you know the distribution, known distribution. Then if you arrange them in uh, increasing order, you get a new distribution for these. This distribution you can find out from using the non-ordered random variables distribution. And these we use to find the conditional distribution of the arrival times. So we found conditional distribution of the arrival times. So we showed that this is the conditional distribution of the arrival time. So you have that we found the joint distribution of S1 to SL given that nt equal to n. So given that in a time interval, you know that n events have happened. Mm, we found the joint distribution of the arrival times of those arrival times of the events. This was the same as um, distribution of the ordered statistics of um, an uniformly distributed random variable in the interval 0, 10. Um, this we showed. We we did the proof for this in the last class, and we we used this theorem uh, to to do some problems on waiting times and finding the expected waiting times of passengers that are about to catch a train, or the expected amount of damage that a device has seen when the damage occurs, when the occurring of the damage is Poisson distributions. So we have seen this. So Next, we'll go to non-homogeneous Poisson process. So in the non-homogeneous Poisson process, so in the homogeneous Poisson process, what you have is you have the mm, expected uh, expected rate at which events occur is the same throughout. It doesn't depend on the time. So it doesn't matter at what time you're watching the experiment or your setup. Every time the same. Uh, every time the same. Uh, the expected number of events that happen in that interval will be always the same. But that is not close to reality, because in close to reality, the the expected number of events that happen is actually time dependent. So suppose you're watching the flow of traffic through a mm, you're counting the number of traffic that passes through a cross junction or some bridge or something. There you see that if it is night time, then the mean would be very low, and if it is morning, you'll have a high amount of traffic that you would expect. So to model that into the picture, you need to make the parameter which decides the uh, expected number of events happening in a time interval to be time dependent. So to more closely model it to the real world, we go to non-homogeneous Poisson process. In the non-homogeneous Poisson process, we have a counting process, nt t greater than or equal to 0 again. Now we say that this to be non-homogeneous, or it is also known as non-stationary. Non-stationary you would understand better, because now the intensity function, now you have an intensity function lambda t such that t for t greater than 0. So for this to be a Poisson non-homogeneous Poisson process, what it needs to have is n0 equal to 0. So no arrival has happened at time 0. And t greater than or equal to 0, this has independent increment, but no stationary increments. Third one is probability of nt plus delta t minus nt greater than or equal to 2 is order of delta t. So what this is saying is, suppose you have a timeline, and here uh, you have t and delta t. So the number of events happening in this interval, the probability that two or more events occur in this interval is of the order of the increment. But now you see you can't write, and yeah, here you can't say that nt plus delta t minus nt has same distribution as n delta t, because at each and every time instant the intensity function changes. So you have a Poisson distribution with lambda t as the intensity function. And the fourth point is probability that nt plus delta t minus nt. So only one event happens in this interval. So the probability that only one event happens in this interval is lambda t. Now the intensity function is function of t into delta t plus order of delta t. So okay, now let us define a uh, function mt. This mt is known as integral 0 to t lambda s ds. Then uh, we need to show that probability of n t plus s minus nt equal to n. So now what you have is you have t and t plus s. So this interval is t. So n arrivals occur in this interval t to t plus s is distributed by, it's a Poisson distribution, but now it will be expectation of minus mt plus s minus mt into mt plus s minus mt whole power n by n factor. Just the intensity function changes. So the expected number of um, events that occur, that term changes. Uh, so the same proof actually carries on from the previous one, but instead of lambda t plus s, instead of lambda just being a constant, now you get it as a function of lambda t plus s. So okay, let us go back to, I think we did it, lecture 5. Yeah, we did here. So yeah, you had so here what we're trying to show is, given the definition 2, we're trying to imply the definition 1. So the definition 1, we showed that from going from definition to definition 1, we showed that we showed this, that um, the number of the probability that n events happen in this interval is Poisson distributed by this. So to show that, we formed it as an recursive equation, and from that recursive equation we got a ODE. And now from this ODE here, we integrated it. Yeah, yeah. From this step to this step, we integrated it. Since lambda was not dependent on t before, so the integration only brought the dt to t. But now, since this is a function of t, here you would get integral 0 to t lambda t. And that integral 0 to t, if you write it as mt. Similarly, you would get one more differential equation where uh, yeah. So similarly, uh, you would proceed, and you now this time you try to find PNS, where you have P n t plus s minus nt is equal to n. But before all this, you need to fix the t, fix t, and then find the probability that n events happen in the interval with length s after t. Just give me a minute. And you actually go through the same expressions again. So first we'll find for P0 of s plus h is equal to probability that number of events occurring, okay, in a small interval delta t, s plus delta t minus nt equal to 0. Now we can split this up in intervals of 0 events in t to t plus s and 0 events in t plus s to t plus s plus delta t. Now independence is there, just stationarity is not there. So you don't have stationarity, but independence is there. And since these both are non-overlapping intervals, you can write them as a product of each. So you have 0 events in t comma t plus s into probability of zero events in t plus s comma t plus s comma delta t. This is zero having zero probability of having zero events in an interval s of length s after t, and for a small interval of delta h you have for 0 you have 1 minus lambda t plus s h delta t plus order of delta t. And now you change around the terms and you get probability of s plus delta t minus probability of s by delta t equal to minus lambda t plus s probability of zero events in an interval s after t order of delta t by delta t. You take the limit and you get uh, you take the limit and this becomes a derivative at of s at minus lambda t plus s into s, because this goes to zero as limit t delta height t goes to zero. So now you solve this, you get log of s is equal to minus integration 0 to s lambda t plus u du. From this we can see that s equal to e power minus m t plus s minus m. So this is the probability that no event will occur uh, at an interval of s after time t. So this all depends because you have fixed the time t. The same you can derive the ODE expressions for P1, P2, Pn, and write as a recursive equation that we did in the last class, and you'll get the same Poisson distributions. So the main important change going from homogeneous to non-homogeneous Poisson process is that uh, in non-homogeneous Poisson process, you can't use the property of stationarity because you allow that in the non-homogeneous Poisson processes, you allow the possibility that the events are more likely at certain times than other times, and the likelihood or the expectation of events occurring at different amount of times that is captured by the intensity function lambda t. So this is on non-homogeneous Poisson process. Okay, so next we'll see compound Poisson random variables. Next we'll see compound. So you have x1, x2, and so on to xn, or let them be a sequence of independent and identically distributed random variables because they're so they are IID. They have the same distribution. Let the distribution be f. And now you have a Poisson random variable n. So n is a Poisson random variable with mean lambda, with parameter lambda. Not Poisson process, just Poisson random variable. Now we define a random variable w such that, and these both are also independent. You define a new random variable such that you add these ID random variables by choosing random number of those random variables. This w is called as the compound Poisson random variable. So first what we would do is we would try to find the so what all is given for you is you have a sequence of random variables, you know the distribution, you have a Poisson random variable n, you know the mean of the random Poisson random variable or the parameter that defines the Poisson random distribution, you know for that of n. Now you want to find a random variable w of this form where you have some random summation of IIT random variables taken from a sequence. So first, what we'll try to find is we'll try to find the moment generating function of W. So here we have expectation of e power tw. This is the moment generating function of W. So to find the moment generating function of W, what we'll do is we'll condition it on n because now it is a sum of mm, sum of random a random sum. So we'll condition it on n. Now n can take any value from 0 to infinity because it's a Poisson random variable. So we'll have summation n equal to 0 to infinity uh, expectation e power tw by condition on n equal to n into probability of n equal to n. This is equal to summation n equal to 0 to infinity expectation of e power t into summation I equal to 1 to n xi. The condition remains n equal to n. But since n is a Poisson uh, distribution, we know the probability that n equal to n it is lambda t power n by n factorial. Next, we have uh, summation n equal to 0 to infinity. Expectation e power p into summation I equal to 1 to n xi. From here to here, we have gone because we know that n and the sequence x1, x2, and so on, these both are independent. So conditioning doesn't matter when the random variables are independent. So we have e power minus lambda t power n by n factorial. Next, we have summation n equal to 0 to infinity. Uh, because each and every one of them have the same uh, distribution, x's are identical. So the exponential of sum, you can write it as product, and you can write this as expectation of e power ex1 whole power n e power minus lambda t power n by n factorial. We know that the moment generating function for x is expectation of e power tx. This is the same expectation for all of the x1 to xn's because they are identical. We can replace the moment generating function here and we can say that expectation of e power ew equal to summation n equal to 0 to infinity. The moment generating function of the random variable power n times minus lambda t power n by n factorial. This will write as exponential lambda t moment generating function minus 1. So this you can write it as an exponential series and this becomes. So now to find the, so now you've got the homogeneity function. Now to find the mm, expectation or the variance, you can differentiate 2.53, or by again using conditioning argument, you can show that expectation of W is equal to lambda into expectation of X, and variance of W is equal to lambda expectation of X squared. Where uh, you know the distribution of X, the distribution of X is F, that is given to you. So the compound Poisson random variable W is how do you generate W is you have um, a sequence of IID random variables whose distribution you know, and you have a Poisson random variable again whose distribution you know. So you add random numbers of the IID sequence that you have, and that random number is generated by a Poisson distribution. Then you end up with a compound Poisson random variable. The expectation of the compound random variable is lambda into e power x, and the variance of the compound Poisson random variable is lambda into expectation of x. So next we have uh, so now we know the compound Poisson random variable summation I equal to 1 to n xi. Uh, so one important property of the compound Poisson random variable is expectation of the compound random process with some function of multiplied by some function of the random variable is equal to lambda expectation of x to hw plus x, where x is the distribution from which you're sampling the sequence. So to prove this, what first we'll find out the so this is a lemma, or this is a property of compound Poisson process. So first we'll find, again we'll do the same thing. Since W is dependent on n, which is the random variable, we'll condition it on n, and then we'll sum it up over all the possible values that n can take, because n is a Poisson random variable. N can take any value between 0 to infinity. So we have expectation of W H W conditioned on power n by n factorial, e power minus lambda, lambda power n by n factorial, into expectation of summation I equal to 1 to n xi into h into summation I equal to 1 to n xi. From the linearity of expectation, you can bring this summation outside. So summation n equal to 0 to infinity e power minus lambda, lambda power n by n factorial. Summation I equal to 1 to n. Expectation xi hi. Summation I equal to 1 to n xi. Now, since all of these have the same distribution, so the expectation is over x size. Now, x size, they are all drawn from the same distribution because they are independent, identical. So you can just write summation n equal to 0 to infinity e power minus lambda lambda power n by n factorial n into expectation x h. Now this is n factorial. So now we calculate this. So here, this term, let me write it down here. Calculate expectation of x h summation I equal to 1 to n xi. So here the randomness is in x. So we condition it over x, but x is, it is a, it could be any random variable which could be discrete or continuous. So I'm doing it for the continuous case. So the same way that we did previous things. So this for x belongs to all the values that x can take. Expectation x h summation I equal to 1 to n xi conditioned on xm can take any number in x into probability that it takes a value x. So this is the conditional expectation that we have. Now, since we know that this takes x, we have integration x into expectation of h of summation j equal to 1 to n minus 1 xj plus x dfx. I'll put this back here and we see that expectation of w h w is equal to lambda integral x summation n equal to 0 to infinity e power minus lambda lambda power m by n factorial into expectation of h summation I equal to 1 to m x I plus x dfx. So now this is the probability that n, the number of, this is a Poisson distribution for n equal to m. So we have lambda integral x summation m equal to 0 to infinity probability that n equal to m, and this is the probability that expect, this is the term that expectation h of w plus x conditioned on n equal to m dfx. Now we have lambda integral x. This whole term is just expectation h w plus x dfx. This whole term is an expectation. So lambda expectation of x h of w plus x. So we got the property that w is lambda expectation of x h w plus x. you can, from this identity, you can actually calculate the moments of uh, all the moments of the random variable w, because now, as you can see, uh, if you substitute h w is equal to 1 everywhere for all values of w, the function h, then you see that expectation of w is equal to lambda into expectation of x. So if you substitute hw is equal to 1, and so this will also be equal to 1 for all values of w, then you can see that expectation of w is equal to lambda into expectation of x, which is the same as what we got here, lambda into expectation. Similarly, you can calculate expectation of w square, and then you can find the variance, which you'll get as lambda into expectation of x squared. To find expectation of w square, you need to put h of w equal to w, so the identity function. Then this will also be w. Then you have expectation of w square is equal to lambda into expectation of x into w, and then you try to come up with. Yeah. So let us maybe try and do that, but we'll do for a more general case where we'll do it for expectation of x wn. We calculate the expectation of wn using the above property that we have got for compound Poisson and a variable. So now let us choose of x equal to x power n minus 1. So we get expectation of wn is equal to lambda expectation of x into w plus x whole power n minus 1. So now we'll lambda into expectation of x. Uh, w plus x is just summation j equal to 0 to n minus 1. N minus 1 choose j. wj x n minus 1 minus j. So we wrote out the binomial expansion of this term w plus x n minus 1. And since w is summation I equal to 1 to capital N, that we'll write in the next step. But now we just wrote the binomial expansion of w plus x whole power n minus 1. Yes, and then you have lambda. Since this expectation, using the linearity property of expectation, now we can interchange the terms, and we have summation j equal to 0 to n minus 1. N minus 1 choose j, expectation of w power j, expectation of x n minus j. Now what we'll do is we'll put n equal to 1, and we will solve these. So what we have is we have expectation of w power n is equal to lambda summation j equal to 0 to n minus 1. N minus 1 choose j, expectation of w power j into expectation of x power n minus j. Now first for n equal to 1, we have expectation of W lambda n equal to 1. There are no summation terms. So j equal to 0 and c equal to 0. Lambda expectation of x. J 0. So this is 1. It will be 1. Um, J 0 is just x power n, but n is 1. Now for n equal to 2, we'll have expectation of W square, which is lambda into expectation of x square plus expectation of W into expectation of x. But from the previous, we know that expectation of W is lambda expectation of x. We have lambda expectation of x square plus lambda square expectation of x square. So like this, you can find all the moments of W. So next we'll define the compound Poisson process. So let us say you have a stochastic processes xt, not a counting process, stochastic process xt, t greater than or equal to 0. Now this is said to be a compound Poisson process if you can write xt as sum of I equal to 1 to nt xi, where nt is a Poisson process and xt is a compound Poisson process. So now the sequence xt is a compound Poisson process. So now this sequence xt is a compound Poisson process. But the value of each term at xt is a compound Poisson randomly. So it's a collection of compound Poisson random variables. Uh, yeah, so we'll stop the class here today. Next class, we'll do some example problems on Poisson process and we'll also start Markov chains. Thank you.